Okay. Okay, good afternoon. Welcome to the second day of ICCP. This is Monday 8th session, the start of the two-day remote conferencing. In this session, we have 4 excellent papers, 2 on de-rendering and 2 on computational imaging. All the videos will be broadcasted online, and please put your questions and discussions. Welcome to the second day of ICCP. This is Monday 8th session, the start of the two-day remote conferencing. In this session, we have 4 excellent papers, 2 on de-rendering and 2 on computational imaging. All the videos will be broadcasted online, and please put your questions.
Hello everyone, I am Jia Juntang from Peking University. I'm here to present our latest work on intrinsic image decomposition, DeRenderNet, intrinsic image decomposition of urban scenes with shape-independent and shape-dependent shading rendering. The other authors of our work are from Beijing University of Posts and Telecommunications and Peking University. So, what is intrinsic image decomposition? Here is a simplified rendering equation. Basically, if we ignore active emission and other complex light transport effects, then the appearance of an object is decided by the reflective property and lighting on its surface. Accordingly, the image intensity captured by a camera can be decomposed into the pixel-wise product of an albedo map and a shading map. There are many recent works on intrinsic image decomposition. Here we list a few of them. Bell et al.'s methods and Nestmeyer et al.'s methods are optimization-based methods and use handcrafted priors, while other methods are learning-based methods and use data-driven priors. Our works belong to the latter type. Unlike most previous works, we focus on outdoor urban scenes. The shadows in outdoor scenes raise a problem, given an image with a big cast shadow. Due to the ill-postedness of intrinsic image decomposition, it's difficult to tell whether the dark region is from the albedo or from the shading. Current works often fail to get shadow-free albedos in outdoor urban scenes, which is the goal of our work. So, here in our work, we first introduce an image formation model for intrinsic image decomposition in urban scenes, and we fully exploit the synthetic data by data preprocessing. Then we propose a 2-stage network architecture for intrinsic image decomposition. At last, we show demonstrations that our method can potentially benefit other computer vision applications. Let's start from the image formation model. Most previous works use this formulation, where I is image intensity, A is albedo, S is overall shading, and epsilon is additive noise accounts for spectral highlight, active light sources, and other outliers. Here we show an example. Now we have the basic image formation model. We further formulate the overall shading as the dot product of the shape-dependent shading and shape-independent shading, where SD is shape-dependent shading. The definition is the dot product of surface normal and hypothetical lighting, assuming no occlusion. SD can be rendered using depth and lighting in our rendering module, where D is depth map and L is lighting of the scene, represented in a latent vector space. SI is shape-independent shading, compensate for the differences between the actual lighting and the hypothetical lighting, which are mainly caused by shadows and interreflections. Here we show an example of shape-dependent shading and shape-independent shading. From now on, we use SD and SI for abbreviations. Our next concern is data. For intrinsic image decomposition, there are laboratory captured datasets containing the ground truth values of albedo and shading. However, these datasets only have limited images and are in object level. The other stream of datasets relies on human annotations. However, the human labels are subjective and may contain errors. Besides, it's hard to use the sparse and pairwise labels in training. Thanks to CG rendering techniques, there are lots of CG-rendered datasets with massive amount of densely labeled images. The images may not be realistic, but are helpful for intrinsic image decomposition. Since we focus on outdoor urban scenes, we choose the FSVG dataset, which is captured from video games such as GTA 5. Since we only have albedo and depth labels, we have to do data preprocessing to get more useful supervision. First, we compute shadow prior map to indicate where shadows might be. Then, we also compute normal to provide explicit shape information. According to our image formation model, we propose the DeRenderNet. DeRenderNet is composed of an intrinsic decomposition module and a rendering module. The intrinsic decomposition module takes an image as input, then extracts global features of the input image using a two-layer network. The albedo and shape-independent shading are estimated separately by residual blocks in albedo branch and SI shading branch, where skip links are used to preserve high-frequency information. The lighting is estimated after a deep encoder and a fully connected layer in lighting branch. The rendering module takes a depth map as input and extracts shape features using a deep encoder followed by a fully connected layer. Then, lighting estimated above are merged with the shape features. The SD shading is then generated after a fully connected layer and a deep decoder. We can use the pixel-wise multiplication of albedo, SD shading, SI shading as the reconstructed image, which is helpful in supervising the training. The loss we use in the training consists of 4 terms. The reconstruction loss is a pixel-wise L2 loss between the reconstructed image and the input image. We only calculate losses on non-sky pixels. The albedo loss is a pixel-wise L2 loss between the ground truth albedo and the estimated albedo. The shape-dependent shading loss consists of 2 terms. The first term encourages surfaces with similar normal to have similar shape-dependent shading, and the second term focuses on shape-dependent shading in probably non-shadowed area. Remember that N is a normal and W is the shadow prior map. The shape-independent shading loss encourages the shape-independent shading to be smooth and dominant in probably shadowed area. Here we show some implementation details of our methods. Please note that depth input are not necessary for albedo and shape-independent shading estimation at inference time. For comparison, we use a group of recent works as our baselines, including both optimization-based methods and learning-based methods. Among them, U19 and U20 also focus on outdoor scenes. Here is a quantitative evaluation on FSVG dataset in 3 commonly used metrics, MSE, LMSE, and DSSIM. To bridge the data gap of baselines, we also retrain U19's methods on FSVG dataset and test its performance. We can see that our method performs best in general. We also do quantitative evaluation on commonly used IIW benchmark. Our method still achieves comparable results on indoor scenes. Here we show some results on FSVG dataset. We can see that our estimated albedo is close to ground truth and is shadow-free, while cast shadows and attached shadows remain in the estimated albedo of their methods. Besides, our method preserves more texture details and avoids oversmoothing the albedo, such as U19's results. U20 has taken cast shadows into account. However, the shadows are not completely removed from their albedo. Here is another example. We also show how U19's method trained on FSVG dataset performs. We can see the colors of albedo are more accurate, however, the shadows still exist. Here are some results on real-world Kitty dataset. We show all shadings in grayscale for easier reference. We can see that our method can also work well in real-world urban scenes. Here's another example. We can see that our albedo can help autonomous vehicles to have a clearer version of road scenes. We also compare our methods with U20's method on Kitty dataset. We can see our method better removes shadows from the albedo. The definition of their shading is similar to our SD shading. We can see that their method fails to detect the attached shadows on the building wall. Here's another example. We can see their methods can only detect and remove part of shadows on urban scenes. We also conduct ablation study on our loss designs. We can see from the results, our method cannot get satisfactory results without SI shading loss or SD shading loss. Here we show some applications of our method. We can cross-render the shape-dependent shading by exchanging the light in the rendered module. From boxed area, we can see the details. The colors of the boxes indicate different lightings. Our decomposition results can also benefit some high-level vision tasks, such as detection. We can see that the off-the-shelf detection algorithm can perform better using our albedo estimation in heavily shadowed urban scenes. Here we show more results on images in the wild, which are collected from Google Street View. Of course, our method has some failure cases, especially with dim night lighting, active light sources, extremely complex shapes, and untypical urban scenes. To sum up, we propose the DeRenderNet to conduct intrinsic image decomposition for urban scenes using our image formation model. Our method can be trained in a semi-supervised way with partially labeled data. Our intrinsic image decomposition results can be helpful to potential downstream tasks. There are limitations of the CG rendered dataset we used in accurately capturing more complex light transport effects, such as specular reflections and interreflections. And that's all. Thank you for your attention.
Okay, thanks a lot for the nice talk. And please post your questions and discussions via YouTube in the live chat. And Jiajun, I have two questions. The first is, the method adopt a two-state strategy, right? Then will the infection in the first stage will be propagated to the second stage?
You mean the arrow propagation?
Yeah.
Oh.
Because there's no feedback from second to first stage.
In fact, in the training stage, the two models in our networks are trained jointly. The arrow signals can be feedback, can be brought back propagated through the feature merging in our network.
Oh, I see. That's nice. And we all know that in urban scenes there are often with a high dynamic range. Will this be a big issue when you're handling the real scenes? I mean, in real application, not synthetic data.
That's true. The high dynamic range problems appears in the urban scenes. In this work, we mainly focus on the buildings and roads, and our main focus is not on the sky region. As you can see, we set the sky region, the pixels of sky regions masked. So in the future, we will focus on the sunlights and other high dynamic range. In the future, we will focus on the sunlight and other high dynamic range.
Okay, then do you have
In the
some
future, we
initial
will
solutions?
focus on the sunlight and other high dynamic range.
Then do you have
In the
some
future, we
initial
will
solutions?
focus on the sunlight and other high dynamic range.
Then do you have some initial
Hello everyone, my name is Ilya Reshetowski. In this video I will present our paper about lensless mismatched aspect ratio imaging. I will start with the motivation for this work. Traditional lens-based camera relies on the perspective projection mapping. The disadvantage of this approach is that the horizontal and vertical scene sampling is limited by the sensor's horizontal and vertical resolution correspondingly. For example, imagine a situation when we need to capture a very narrow horizontal scene with a standard sensor. To capture such a scene, we can choose a lens with sufficient field of view and crop the resulted image. Or even use an anamorphic lens to stretch the scene image along the vertical axis. However, in both cases, horizontal resolution will not exceed the horizontal resolution of the sensor. We propose to solve this problem by changing the scene sampling aspect ratio with a lensless camera equipped with a specially designed mask. The mask design is chosen such that each scene point is encoded by a different sub-area of the mask. To achieve this mask property for imaging a scene with resolution px cross py by an x cross ny sensor, we use an nx plus px minus 1 cross ny plus py minus 1 mask. The scene image is then reconstructed from the sensor image by inversion process. Since our lensless camera requires a reconstruction step, the mask design plays a central role in the final image quality and in the complexity of the reconstruction algorithm. We build our masks by folding one-dimensional binary sequences with good cyclic autocorrelation properties. For mask folding, we use generalized folding procedure proposed by Luque et al. In 1997. The folding process is outlined on this slide and relies on equations 1 with the parameters ax, ay, and d. Luque et al. Proved that if the conditions for the folding parameters described by equations 2 are satisfied, then any 2nx minus 1 cross 2ny minus 1 sub-area of the infinite displaced periodic array has the same two-dimensional cross-correlation properties as the initial 1D sequence. For example, if the conditions 2 are satisfied, the submask indicated by the green rectangle will have such a property that any two nx cross ny areas inside the rectangle will have their cross correlation equal to some autocorrelation of the 1D sequence S0. Conditions 2 allow to construct optimal masks for regular lensless cameras with px equal nx and py equal ny, but they are not sufficient to make masks with mismatched aspect ratio imaging, when px not equal nx. In our paper, we provide additional conditions for generalized folding in case if the dimensions of the scene and the sensor don't match. These conditions are listed in equation 3. In other words, if conditions 2 and 3 are satisfied simultaneously, any px plus nx minus 1 cross py plus ny minus 1 submask taken from the infinitely displaced periodic array has a property that a lensless mismatched aspect ratio imaging process through this mask can be described as a one-dimensional cyclic convolution of the scene points with a 1D binary sequence S0, as shown in Formula 4. Here O is a px cross py scene, I is an nx cross ny sensor image, and P2D to 1D is a 1D permutation of the flattened 2D image, and P1D to 2D is a 1D to 2D reshaping permutation. Equation 4 allows us to use one-dimensional cyclic deconvolution methods to reconstruct images encoded by our masks. This is already great, but the folding process introduced above is independent from the basic 1D sequence S0. Therefore, we can choose S0 to have good deconvolution properties. In our paper, as a basic 1D sequence, we use uniformly redundant arrays, or URAs, binary sequences with constant autocorrelation side lobes. These sequences have very good deconvolutional properties and allow to reconstruct the signal by cross-correlation with a mask, which can be efficiently implemented using fast Fourier transform as shown in equation 5. Here A is a mask and F is a two-dimensional discrete Fourier transform. With this result, our imaging pipeline is as follows. At first, the mismatched aspect ratio scene image is captured by our lensless camera. The result is a single sensor image, which is then used as an input to our Fourier transform-based reconstruction algorithm. Then, we use a U2net CNN to refine the result. To validate our theory, we built two prototypes. Our first prototype is a wide aspect ratio lensless camera designed for imaging scenes with resolution 3171 x 103 using a 453 x 721 sensor. To make the mask, we took a sparse Zinger-Ura sequence with about 300,000 elements and folded it into 3623 x 832 mask with the parameters satisfying our folding conditions. The mask appears black on the slide because it's very sparse. However, a zoomed view on its part reveals the underlying dotted pattern. Sparse mask was chosen to avoid the diffraction crosstalk, and to improve the image sharpness and light efficiency, we substituted transparent features with Fresnel zone planes. The final mask is approximately 50% transparent and has the same PSF as the initial mask. Here is the photographs of our prototype. On the left is a picture of our lensless camera, and on the right is a picture showing the TV used for displaying pictures for CNN training. The white stripe on the TV indicates the field of view of the lensless camera. In this prototype, the sensor is oriented vertically, making the theoretical horizontal resolution of the scene 7 times larger than the horizontal resolution of the effective sensor image. For CNN training, to match the aspect ratio of our scene, we modified Kitty dataset by concatenating random frames at random locations. Our dataset has around 10,000 images. For the training, we used around 7,000 images. After capturing the scene with our lensless camera, we perform the initial reconstruction using fast Fourier transform. Then, for a final result, we apply the CNN refinement. For a better comparison, we zoomed in different areas from the refined and original images. It is possible to notice that the reconstruction quality is slightly reduced near the left and right edges of the result. This degradation is caused by the sensor's angular sensitivity falloff. On this slide is a reconstruction example of a real scene together with a photograph of the scene captured by a high-resolution camera. Our lensless mismatched aspect ratio imaging principle is flexible with scene and sensor dimensions. For example, it can also be applied for imaging of a nearly square scenes with a very narrow sensor. Also, because of the periodic property, we can simultaneously encode adjacent subsensors areas by using as a mask a bigger part of the infinite displaced periodic array. In combination with the standard rolling shutter sensor and using the idea proposed by Antipa et al. In 2019, we can achieve a fast frame rate effect. The advantage of our method over the existing ones is that each subframe is encoded with the same one-dimensional sequence, which allows to reconstruct them independently and efficiently. To confirm these findings, we constructed a high frame rate lensless camera designed for scenes with resolution 217x169 with 33 sensor sub-areas of size 31x1183. This arrangement allows to achieve 33 times frame rate speed up from 60 to 1180 frames per second. To make the mask, we took a sparse Zinger-Ura sequence with about 40,000 elements and folded it into 1241 x 1351 mask. This time we used a smaller Sony IMX178 rolling shutter sensor, which allowed us to reduce the distance between the mask and the sensor to just 1 millimeter. This video is a compilation of our fast frame rate results for various scenes. Each sub-video was generated from 33 frames independently reconstructed from a single sensor image. In summary, we have developed a novel lensless mismatched aspect ratio camera. Our solution is computationally efficient and robust to noise. With our first prototype, we have demonstrated that our method allows to achieve significantly larger horizontal resolution than the original sensor's horizontal resolution. With our second prototype, we have demonstrated that our method can be extended to simultaneous and independent imaging of the same scene with multiple sub-areas of the sensor. This is the end of our presentation. Thank you for your attention.
Okay, many thanks for the nice presentation. This encoding scheme is quite clever. My question is there an upper bound for the difference of the aspect ratio between the FOV and the camera sensor? For example, is it possible to use a lens scan sensor?
Basically, the aspect ratio differences introduce the requirement on the size of the mask. So if our aspect ratio difference is extremely large, then the mask will be also extremely large, and it will also require larger distance between the mask and the sensor, and focusing becomes more problematic in the situation. So in this case, it really depends on the combination of the aspect ratios.
Okay.
But theoretically, it's possible. Any combinations are possible.
Mm-hmm. Then how about the extension to longer wavelengths? Because for some longer wavelengths, usually we have some lens scan sensor or some sensors with limited pixel number.
Actually, it's a good suggestion, and I think with longer wavelengths, it can be very advantageous to use this technique. And for example, you can sense two-dimensional scenes with line infrared sensors. And yeah, I think it's quite possible to use this technique for these applications.
Mm-hmm. There's one question in the live chat. How would you relate your work to lens sensor-based cameras?
Oh,
okay.
I think is I guess connected with previous work based on positioning multiple line sensor for 2D sensing. But in our case, we can do 2D sensing with a single line sensor, basically, using our folding method.
Mm-hmm. Okay, let's
There's
leave the, okay, because the time is limited, we can leave the questions and answers to the live chat, okay?
Thank you very much. Thank you.
Okay, then before the third speaker, I will give some brief introductions about ICCP. Maybe some audience is not quite familiar with this field. Computational photography is an intersection of disciplines involving imaging optics, sensors, signal processing, computer vision, and graphics. We'll seek here creation of new photographic and imaging functionalities and experiences. We want to go beyond the exclusive disparate camera and image processing technologies. Okay, now let's start the third paper. The third paper is from Korea Advanced Institute of Science and Technology. The title is View-Dependent Scene Appearance Synthesis using inverse rendering from light fields. Okay, please play the video now.
Hi, I'm Dahyung Kang from KAIST. This is a collaborative work with Daniel Jeon, Ha-kyung Kim, Hyun-jung Jang, and Min H. Kim. I'm going to present our recent work, View-Dependent Scene Appearance Synthesis using inverse rendering from light fields. Light fields are snapshots of light rays flying in the air. Conventional camera captures 2D projection, which is an integration of light fields within its field of view. Light fields camera captures 4D parameterized information of the light rays, including the directional information as well. As light fields being high-dimensional, it is popular to parameterize light fields with a two-plane coordinate system. A light ray can be represented by a pair of the coordinate in the sensor side plane ST and the coordinate in the object side plane UV, and this can be used to represent each light ray. A slice of this two-plane parameterization with a fixed sensor side coordinate ST is called subaperture images, and this can be seen as conventional 2D camera projections. By preserving those whole light ray information, we can synthesize refocused image with a larger virtual aperture. Among previous works on depth estimation in light fields, many works assume diffuse material and enforce photometric consistency. Pozo et al. Proposed a matching-based method for 360 depth estimation from fisheye images. Few works devised appearance-aware depth estimation in light fields by jointly optimizing geometry and reflectance. Wang et al. Employ a differential approach on objects captured by micro-baseline light fields camera. No et al. Use an iterative method to ease Lambertian assumption. Both works are suitable for micro-baseline light fields in object scale and hardly extendable to indoor scenes. State-of-the-art view synthesis method in light fields construct multiplane images and then blend them. Starting from stereo MPI-based view synthesis of Ju et al., Mildenhall et al. Extended it to light fields using multiple MPI frustums, and Broxton extended it to multispheres to provide immersive experiences. Plane blending methods are effective for detailed view synthesis. However, as they force to bake all of the reflection and appearance property into the geometric representation, their applications are hardly reachable to scene addition or relighting. In this work, we propose an inverse rendering algorithm to estimate geometric properties and represent view-dependent appearances from wide baseline light fields of indoor scenes. First, we capture light fields and estimate the geometry. Initial depth is refined iteratively using diffuse specular separation. Then the appearance is estimated by optimizing normal and reflectance, finally conducting view synthesis. We built on wide baseline light field acquisition prototype with 4x8 machine vision cameras equipped with fisheye lenses of 185 degrees of field of view. This device provides synchronized capture and data transfer over a local network. Microprocessor called Jetson Nano manage all of the acquisition configurations and data. These sub-aperture images are indoor scenes captured by this prototype. In the geometry estimation stage, we estimate the initial depth first under diffuse assumption. We use optical flow from loft to get corresponding points among sub-aperture images. Unprojected corresponding points would converge to a 3D point, but maybe not exactly. Thus, we find a point that minimizes the squared error distance to all of the camera rays. This can be formulated as a matrix form least squares problem. Using that initial depth, diffuse and specular components are separated from input images. Diffuse reflection is estimated by the minimum intensity among warped views, and by subtracting the diffuse image from the input image, we get specular reflection. To refine the initial depth map, a depth disagreement map is calculated by summing the squared distance to the camera ray using the previous formula. Owing to the specular reflection, our depth estimation fails, resulting in high residual errors in the depth disagreement map. Those are filled by another depth estimation on diffuse-only images. Although the initial depth map is based on diffuse assumption, depth error by specular reflection is gradually relaxed by our iterative approach. Based on the estimated geometry, we begin with inverse rendering that includes normal and reflectance estimation. This figure shows aluminum tape on a plate and pixel intensities at the green dot location captured by each camera in a grid of 4x8. Plotting the pixel intensities in object space shows the reflection distribution of the aluminum tape. The reflection distributions differ by surface roughness of materials. Aluminum tape presents very small diffuse reflection and strong specular reflection in contrast to rough surface. Plain-form model is one of popular reflection models. According to normal, incident light direction, outgoing direction, and halfway vector, the reflection ratio is determined. Parameters for this model are diffuse albedo, specular albedo, and specular smoothness. Our image formation model is discrete summation over light sources. For each light source, take a reflection ratio of incident light power. With the captured pixel value, we then evaluate unknown parameters in our image formation model. Here, the light sources are estimated from an HDR image at the center view and subsampled to construct a set of point light sources. These are known variables in our image formation model, and these are unknown. Our problem statement is to find those unknown variables that minimize the total loss given known variables. For the sake of practicality, we cluster surface points and assume shared diffuse albedo, specular albedo, and smoothness per cluster in order to increase the number of angular observations. Total loss is a weighted sum of rendering loss and normal smoothness loss. Rendering loss consists of diffuse and specular loss, where the diffuse loss is L2 error between the observed and rendered diffuse component, and the specular loss is L2 error between the observed and rendered specular component. The normal smoothness loss is defined as Laplacian of surface normal. We solved this using Adam optimizer over 500 iterations. Now we demonstrate our result of geometry estimation. We quantitatively compare the geometry accuracy using synthetic scene, where photoether and teether present higher depth errors in specular region. Ours shows more accurate depth result. This is result from real scene. Our method shows plausible depth values on diffuse surfaces. However, photoether presents artifacts on specular reflection where the photometric consistency assumption breaks down. TID-ether shows inaccurate depth estimation on the specular reflection on the floor, and our method demonstrates smooth depth refinement on that region. Now we demonstrate another result from a scene with a strong specular reflection. Next, we present our appearance estimation results. Diffuse and specular components are separated from input images, and our appearance estimation algorithm successfully reconstructs the diffuse and specular component. Finally, we demonstrate our view synthesis result. In this synthetic experiment, our algorithm synthesizes reflection close to the ground truth, even at unseen viewpoints. In experiments with real scene, the moving reflection on the floor is realistically synthesized while keeping correct geometry. Compared to the other methods, specular artifacts of photoether and over-smoothing artifacts of Miltenhall ether are eliminated in our inverse rendering-based method. By selecting subsets of input views, we evaluate interpolation and extrapolation results of our method compared with other methods. Ours preserves the specular effect while not over-smoothing the appearance. This highly specular scene is especially hard due to its mirror-like behavior. While others lose specular appearance, our method managed to reconstruct specular reflection. Unlike other view synthesis methods, ours also enables scene appearance editing applications. We can change the specular roughness of the material and remove or add light sources, thanks to the decomposition of the appearance and geometry. Our method is not free from limitation. We cannot estimate specular components on points that have not shown specular reflection at all views. Our image formation model lacks of global illumination, thus overestimates diffuse albedo on the ceiling. The lighting is restricted to a set of diffuse point light sources, and our method cannot express metals or anisotropic material. Also, there is dependency on hyperparameters such as the number of clusters. To conclude, from wide baseline light fields, we propose a depth estimation method robust to the specular reflection employing diffuse specular separation, and our method can synthesize view-dependent appearance through inverse rendering in scene scale. We also demonstrate various applications of scene scale appearance editing. Thank you for listening.
Okay, thanks for the nice talk. Then Dayun, I have some questions. It's quite interesting. My question is, will fish islands will impose some extra challenges compared to some Euro lenses?
So we use the fish islands for the wide field of view capture, but obviously it took some not ordinary efforts, such as the non-perspective matrix multiplication, but we should use the radius normalization. So yeah, it took some extra works to work with that fisheye lens compared to the perspective lens. Yeah.
And I also noticed that the specular regions are usually isolated in your examples. Can you handle the specularities with some overlapping regions, overlapping areas? For example, the two highlights of large area and they intersect.
Yeah, that in theory that makes sense because we are taking the discrete summation over the all light sources. Yeah, and that I think that is a good suggestion for more experiments on our method. Yeah, that's good suggestion.
Okay, here is a question from the audience. How would you go about incorporating global illumination effects in the future? Can Monte Carlo rendering help with that?
Yeah, that's very good question. And incorporating global illumination effects is very important feature. So, but Monte Carlo rendering takes some like heavy computation, I guess. So maybe using some approximation on it, like speaker harmonic, something like that makes sense. But yeah, Monte Carlo rendering may help with it. I think so.
Okay. There's another question. How does the proposed approach compare to neural reflectance field-based approaches, the NeRF-based approaches?
Yeah, NeRF-based approach is very hot topic in this season. So yeah, I also looked at that paper, and basically that paper works on 3D volumetric space. So kind of similar theme, like optimizing the surface properties. But yeah, I also looked another paper deviated from the NeRF, which is trying to recover the reflectance information in addition to the occupancy information. So yeah, that is two different approach to the 3D data, I think.
Okay, no further question. Let's move on to the next paper. And before that, recall that we have a virtual poster session right after this session. That is, after this coming talk, we can meet and interact with each other on the virtual floor of the posters. The virtual space is GatherTown. Please see our website now for information about how to log in. Okay, see you there. And now, let's start the first talk. This work is from the group of Shanghai Tech University entitled MirrorNeRF, one-shot neural portrait radiance field from multi-mirror catadioptric imaging.
Hi, I'm Ziyu Wang from Shanghai Tech University. Today I'm talking about the MirrorNeRF, one-shot neural portrait radiance field from multi-mirror catadioptric imaging. Photorealistic overview synthesis is critical for numerous VR applications. Existing solutions achieve high rendering quality, but require either a stationary subject or a multi-camera system, which is heavily capturing in space and time. The one-shot solution to get rid of the tedious multi-view synchronization and calibration remains extremely challenging. At the same time, the catadioptric image system combines the camera and the mirrors to capture a wide field of view, and the multi-mirror system can be analogous to the multi-view system, which potentially allows 3D modeling of a scene through only one-shot capture. Previous works enable one-shot 3D reconstruction by using multi-stereo technicals, but only a coarse geometry can be recovered. Other methods use the system to capture a wide-angle light field, but they still suffer from unrealistic blending artifacts due to the discontinuity of the recovered geometry. To tackle these challenges, we extend the neural radiance field into the catadioptric imaging, using the multi-mirrors to strengthen the neural radiance field generation. So we can provide one-shot photorealistic rendering. Here is our system setup. Our system consists of a high-resolution camera, a spherical mirror array, and a printed A3 size calibration paper. We scan the geometry of the mirrors in advance and arrange them into the hexagon of our honeycomb calibration pattern. To calibrate the system, we assume all the mirrors are put in the exact place. So, once we get the transformation from the calibration plane to the camera, we can obtain a rough estimation of the mirror positions. Here we show more details. From the captured image, the pixel coordinates assign each pixel a value of UV. As for the calibration pattern, it has a local system XYZ. For each red dot on it, it has a lower coordinates xi, yi, and 0 on the z-axis. Then, given 4 pairs of correspondence from the captured image to the calibration pattern, we can estimate the homography transformation H. Then, we left product H by the inverse of the intrinsic matrix K. The transformation matrix between the image plane and the calibration pattern can be extracted by normalizing the first column of it. Finally, we use the orthogonal proclusters to get the final rotation matrix. After that, we cast the rays from the camera to calculate the ray-mirror intersection. Then, we can restore the reflective rays using the law of reflection. And we use the corresponding pixel color as the ground truth for the network training. With the restored rays and the ground truth color, we can feed it into the original pipeline of the neural radiance field. We sample 3 reading points from the rays and pass them into the network. The network will output the density and the color of each sample point. Accumulate all the points along the ray by volume rendering, we can get its final RGB color. Then the color difference between the ground truth and the estimated color will propagate to the network weights. However, due to the misalignment of mirrors caused by our manual arrangement and the rough calibration, the rendering results from the neural radiance field shows strong blurring. To alleviate this problem, we propose the warping displacement field. It takes 2 elements as input. One is the point position, the other is the learnable per mirror latent code, which modulates the warping field to the different mirrors. The network will output a warping displacement ΔS for each sample point. Then we set the warped point as the input to the neural radiance field and train the 2 networks within the same color loss. After training, the sample point position is directly fed into the neural radiance field for overview synthesis. Here we show the comparison. With the neural warping, we take the misalignment caused by calibration error and rendering a more photorealistic image. However, there are still some problems in our setting. Unlike the traditional neural radiance field that takes multi-image as input, all the rays in our setting are more concentrated. We lack enough rays from the back and the side to supervise the regression. It will easily cause degraded results. To tackle this problem, we propose 2 density regularizations. The first one is the implicit viewing hall. For each mirror in the captured image, we segment it into the foreground and the background. For rays corresponding to the foreground, it takes the previous pipeline and calculates the color loss. But for rays corresponding to the background, we only query its density from the network and using the viewing hall loss to force the density to be 0, which regularizes the density in the background. However, it cannot handle the space in front of the object and will produce an extra implicit convex hall. In that region, even point has a low density level. It is enough to cause noisy rendering results. To tackle this problem, we propose a self-supervised approach to regularize the density in that region. for the ray that corresponds to the foreground, we query all the density of the point along this ray. Then, we define a threshold tau to filter the noise with low density. After that, we use the filter density to calculate the accumulated depth. For sample points that before the accumulated depth, we use the geometric aware loss to force their densities to be zero. Here we show the comparison. Without density regularization, we can observe some noise in some regions such as hands and eyes. However, with our density regularization, we obtain an image with photorealistic rendering quality. Now we finish our algorithm, we show more results. These are free viewpoint videos rendered by our approach. Here we show some comparison. We compare our method to per voxel color and the neural radiance field. Our method achieves the best rendering quality. At last, we show some evaluations of our system. We first evaluate the influence of the number of mirrors. We only use the reflected rays from selected 5, 11, 17, and 25 mirrors to train the model. We can see that the rendering quality declines and some artifacts appears when we decrease in the number of mirrors. Another evaluation is to demonstrate our system is unstructured. We capture the data of the face mark from 4 different angles. Then we train a network for each view. Here we show the rendering results and the training curve. At normal capture angles such as view 1, view 2, and view 3, our system gets similar results. Only at some particular skewed angle such as view 4, the rendering quality will be degraded. An additional advantage of our catadioptric system is the video rate capture. Here we show the video sequence results. Our system efficiently avoids the temporal artifacts and can easily capture the dynamic sequence without tedious camera synchronization and calibration. To summarize, we present the first approach to combine neural radiance field with catadioptric imaging, which enables one-shot, photorealistic, and free viewpoint human portrait rendering. Our lightweight catadioptric system enables diverse ray sampling in the 3D space, which is low cost, easy deployed, and supports carrier capture. Our neural warping radiance field enables implicit compensation of the misalignment due to our flexible system setting via a continuous displacement field learning. Our density regularization provides more efficient density supervision for higher rendering quality. That's all. Thanks for your attention.
Okay, thanks for the next presentation. And the author of this paper will answer the questions without video. Here we have one question from the audience. How large resolution do you require? Do you get better results with more mirrors?
We actually use a camera of resolution 1900 times 1600. It's actually about 16 million resolution, since we need to capture all the mirrors in one photos.
Okay. And do you get better results with more mirrors?
Yeah, of course.
Okay. I have one more question. The method is of impressive results. I'm wondering how to set the surface curvature of the mirrors. I think we need a trade-off.
We actually use the 3D scanner to scan the geometry of the mirrors, and we all the mirrors as spherical mirror. So we only need to know its radius, to know its coarse geometry. So then we can calculate the basic reflection for the further optimization.
I mean, how do we choose the curvature? We should use a flat ones or some curly ones.
It's we use spherical mirrors, so it's actually has a lower curvature once we scan the geometry of it.
Okay, then this setup is targeted for portrait, the portrait rendering. Can it be easily scaled to some larger scenes or larger objects?
We didn't test to apply it for the large object, but the setting is useful. But the setting can be easily adapted to the large scenes.
Yeah, this is a general method, right?
Yeah, just keep the arrangement of the mirrors. But in this paper, we focus on the Perchin rendering.
Okay, I see. Okay, thanks again for your nice talk. Now that's all the 4 papers for this session. Thank you for nice presentations from the authors, and thanks for the attendance from the audience online. And at last, thanks a lot for the hard work from the organizers and the volunteers, which is more difficult to organize an online conference than the offline ones. Okay, thank you all again.